Next, let's talk about projecting one vector onto another vector. And this is helpful, particularly if we're trying to break things down. So for instance here, we've already learned how to add two vectors to get the resultant vector, right? So I'm just doing the force example that we've seen before. So you can add two vectors to get a resultant vector, right? And these are called vector components. But it actually helps to use projections to go backwards. So maybe you have the resultant force, but you need to work backwards to the two forces that were added, or you have the resultant vector, it doesn't have to be a force, and you work backward to the two vectors that were added. That's when projections can be the most helpful. So how do we work with projections? So visually, here I have just two examples. So excuse my drawing, I was trying to make it a little bit longer here. So my initial vector is V here, and then my other initial vector is the W, so in blue and in pink. And then to project that vector onto W, notice because this is an acute angle, it lies right above it. So you almost like mirror it down on top of the W, but you do that using a 90-degree angle. So we have to draw a point sort of down from here to here to figure out how that falls. So this purple would be the projection. So it's almost like taking this and putting it on top of the W. Here you have an obtuse angle. So our original vector is the blue one, and then our W vector is the pink. So you have an obtuse angle, something bigger than 90 degrees. I know my drawing is not great. And here again, that W is going the other side. So you don't project backwards here. You're still going to project down, but we use the opposite direction here. And again, we still use that 90-degree angle, and we're able to get the projection of W, of V over W, excuse me. So we're projecting V onto W here. So those are just two visuals of what's going to happen. Now we have a formula as well that we can use, of course. So let's say that V and W are two non-zero vectors. What is the formula for the projection then? Of V onto W, right? So it depends on which way you're going. So V onto W. This is the notation here, and I use this up here as well. So we're going from V onto W. So V is kind of like the main one. You see it up top here. Well, you take the dot product of the two, you divide it by the square of the magnitude of W, and then you multiply that as well by the W vector. So let's do an example here because it's a little tricky. All right. So let's let V be the vector 2i plus 4j, and W the vector negative 2i plus 6j. And we're going to find the vector projection of V onto W. And it is important to know what's getting projected where, right? So we're doing V onto W because the ordering is important here. So our formula is going to be as follows. So let me move this out of the way. So we start with our dot product here for this piece. So actually, let me just do some of these steps out, I think, off to the side. Let's start with that dot product. So we're going to multiply the 2 times negative 2 and add that with the 4 times 6. So I have negative 4 plus 24, which is 20. So it's going to be 20 here. And then let's work out this as well. So I'm going to start with just the magnitude of W. So I'm going to take the square root of a squared, negative 2 squared plus 6 squared. So 4 plus 36, which is 40. So 2 root 10. And actually, I didn't even have to do all that work because I'm going to square this anyway. So let me make my life easier. I'm going to go back a step. I'm going to square it. Instead of simplifying, let's use this one, right? Square root of 40 is the same answer. And when I square that, my square root just cancels. So I have 40 there. And now I'm going to plug that back in. So I have 20 over 40. And then I also have my other vector here. So my vector that I'm multiplying is negative 2i plus 6j. So what happens is this piece out front becomes a scalar multiplier. So this right here, this becomes a number. It's going to be a scalar multiplier. So here I end up with 1/2. So I'm going to distribute that 1/2 all the way through. And what I get is negative 1i plus 3j. And again, you don't really need that negative 1. Bring in a little bit of room here, but you could also write it as just negative I plus 3j, and that would be fine as well. So that would be the formula for the vector. That's the projection of v onto w. So it's a little bit of work, a little bit of algebra, but really it's not too bad. So this is a scalar here. Everything's going to come down to just a number, and then you're just going to have a scalar multiplier by that remaining vector. So I said that this was most helpful when kind of working backwards and trying to find the original vectors that are being added. So let's look at that here. So I'm going to have a definition for you guys. Let v and w be two non-zero vectors. Vector v can be expressed as the sum of two orthogonal vectors, call them v1 and v2, where v1 is parallel to w and v2 is orthogonal w. So v1 is equal to the projection of v onto w. And we just saw the formula for that, right? The dot product of v and w for the square of the magnitude of w times the vector w. And then the second vector is going to be v minus v1. The first one's the hard one to find, and the second one is the easier one to find. So we can take a vector and we can break it into the sum of two other vectors. And the first one uses that projection formula, and the second one we can find just by subtracting. So let's do one last example on this topic. So let v be 2i plus 4j and w be negative 2i plus 6j again. And we want to decompose. So decompose means to break it back down. So sort of like uncombine it. V into two vectors, 1 and v2. Where v1 is parallel to w and v2 is orthogonal to w. So basically that just means just use this formula here. That's really what we're telling you to do. So we're breaking it down in a very specific way, right? Because obviously you could break things down in many ways. This is a very specific way. Now, these are the two vectors we've already used. So I already know v1, because I've already found the projection of v onto w from above. And if we just scroll up here, I have the answer already. It was negative I plus 3j. And then I can find v2 by taking v and subtracting v1. So my V here is 2I plus 4J. I'm going to subtract that with V1, which is negative I plus 3J. So I'm going to go ahead here. I have 2 minus negative 1. So 2 minus negative 1 for the I, and then 4 minus 3 for the J. So I have 3I plus 1J. And that would be my second vector. So here we have our original vector. We have broken this down, we've decomposed it. One of the breakdowns is this vector here, and the other one is this one. So what you're doing here is you're saying that, okay, that original vector is being broken into that first vector, this one, and then your second vector. So this is your first vector, and this is your second vector. And if you check this, if you add those back together, you should get the original, right? If I look at 3 plus negative 1, there's the 2, and 1 plus the 3 is the 4. So you can always check by adding them back together to make sure you have broken them down correctly.